Well, first of all, a big thanks to the organisers for arranging what's already proving to be a great conference. Today I'm going to be speaking about some joint work with Dylan McDermott, and there are going to be two aspects to this talk. So the first aspect will be the theory of relative monads, and the second aspect will be formal category theory more generally. And so I'm only going to speak about some new results right at the end, and my my hope for this talk is I give you some idea of the motivation for us working in a setting that we do, which will hopefully get you interested in actually taking a look at the paper and speaking to me afterwards. So first of all, let me tell you what a relative monad is. So to do so, I'm going to first introduce the concept of relative adjunction, which is slightly simpler. So a relative adjunction is a generalization of the concept of adjunction, where we allow the domain of the left adjoint to be different from the codomain of the right adjoint. So if you take a look at the diagram at the bottom of my slide, you see to do this, I've added an extra functor j at the bottom, and I'm going to ask for an isomorphism of Hom sets, like in the typical definition of adjunction, except I'm going to ask that morphisms from Lx to y are in natural bijection with morphisms from Jx to Ry. And so this is an old concept, but it's maybe less well known than it ought to be. Now, there are many examples of relative adjunctions in category theory, but often they're not phrased explicitly as relative adjunctions, which is why they may not appear as common as they really are. So every adjunction is truly a relative adjunction, something interesting. A very common class of relative adjunctions are partial adjunctions, so we ask for the functor j to be fully faithful. So for instance, a category with only some limits or co-limits, this property can be expressed by a partial adjunction rather than an actual adjunction. Multi-adjunctions, in the sense of Diaz, are relative adjunctions. The universal property of a weighted co-limit in rich category theory is an example of a relative adjunction. The universal property of the nerve functor associated to some functor is a relative adjoint functor. And there's a very natural way in which we can see algebraic theories and their various generalizations to enrich category theory as examples of relative adjoint functors. So I really just want to give you the impression that these are all over the place, so they're worth studying. Now, just as there's a tight connection between adjunctions and monads, so too is there a corresponding notion of relative monad. So the idea behind a relative monad is we want to generalize a monad that the underlying functor doesn't necessarily need to be an endofunctor. So these were introduced fairly recently, or about 10 years ago, and for the most part they look very similar to the definition of a monad. So you see the first thing we've done is we've introduced this functor j as before, and this is going to act as a sort of identity functor for our relative monad in some sense. Now the next two pieces of data are very familiar from the definition of a monad. So you have some underlying functor, but now it doesn't have to be an endofunctor. It has the same domain and codomain as j. And we also have a natural transformation, the unit, which goes from j to t. And so this is a sort of sense in which j is acting like an identity functor. Now the thing here that's different from a monad is that we don't have a multiplication operation, but we have what's called an extension operation. And so what this does is it takes morphisms from jx to ty to morphisms from tx to ty, all x and y. And this sort of encodes the universal property of being a free object in some sense. Now we ask for this data to satisfy associativity and unitarity axioms, just like a monad. But if you've never seen this definition before, well, it sort of looks similar to the Kleising presentation of a monad, which might be more familiar. But even if this looks completely strange, don't worry about it, because we're not really going to use this definition for the rest of the talk. The one important thing to note is that when we take j to be the identity functor, this data is actually equivalent to the data of a monad, and that's not entirely obvious, but it is the case. Now, just as relative adjunctions are very common in category theory, so too are relative monads. So I've just mentioned that monads are trivial relative monads. We also have a notion of partial monads. A more interesting example, which it doesn't correspond to one of the examples I showed for relative adjunctions, are graded monads. So there's a notion of monads graded by some monoidal category. These are examples of enriched relative monads. Now, every monad can be seen as a trivial relative monad, but also some classes of monads can be seen as non-trivial relative monads. And it's often helpful to do so. We can prove things more cleanly by working with relative monads rather than their corresponding monads. So for instance, every finitary monad on a locally finitary presentable category is an example of a monad relative to the inclusion of the finitary presentable objects. And this is a useful thing to want to do. And then another example is that monads that arise from monad theory correspondences in a very general sense. It's typically useful to think of these as relative monads rather than ordinary monads. But I'm not going to go into any of the details of these examples in this talk. Again, I just want to give you the impression that these things are all over the place and we want to study them. So now we can get to the motivation for the talk and for the paper I'm talking about, which is that the theory of ordinary relative monads is actually quite well developed. So although the modern definition was introduced recently, there are special cases that go back much earlier in the literature. And so together all of these works have built up quite a good corpus of results for using manipulating relative monads. However, as I mentioned, and there are more examples I didn't mention, there are many examples of relative monads in enriched category theory that we'd also like to study. And so I'd like a development of enriched relative monads. That's the motivation for this talk. However, to develop a theory of enriched relative monads, we need to decide what we're going to enrich in. And this is going to lead to sort of a rabbit hole. So the typical choice of a base of enrichment, sort of following Kelly for instance, is a complete and co-complete closed symmetric monodal category. And this is very nice because a lot of constructions in enriched category theory become simpler when we have all these assumptions. However, it turns out that a lot of enriched category theory, and in particular the theory of enriched relative monads, doesn't require any of these assumptions, or requires very few of these assumptions. So we could also decide to enrich in an arbitrary monodal category. However, especially once you drop the symmetry requirement, the theory of categories enriched in monoidal categories is very similar to the theory of categories enriched in bicategories. And at this point you may be wondering why we're just needlessly generalizing, but in fact we do have interesting examples of relative monads that are enriched in bicategories. So we have examples we're motivated by considering this sort of generalization. But there are also other more general forms of enrichment we could consider. So we could consider enrichment in virtual double categories, skew monoidal categories, and there are others besides. So at this point we've got sort of a lot of different choices, and it's not clear what we should choose. However, suppose that we did find some base of enrichment we were happy working with. It covers all of our examples, we can prove the theorems we were interested in. This would be fine for a while, we might be happy. But before too long, we're inevitably going to find examples that don't fit within this framework. So we might find examples that don't live within enriched category theory. So for instance, we might find ourselves with examples of internal relative monads, or fibered and index relative monads, or monoidal relative monads, or so on. And this brings me to the second part of the talk. So what is formal category theory? So the idea behind formal category theory is that within category theory as a subject, we have many different flavors of category theory, some of which I just mentioned. So ordinary category theory, enriched category theory, internal category theory, and so on. And in each of these flavors of category theory, we generally have the same definitions and theorems. So for instance, we usually have some notion of adjoint functor theorem, we have monadicity theorems, a theory of accessible and presentable categories, we have theories of pre-sheaves and co-completions, and so on. And as category theorists, this should strike us as being dissatisfying, because category theory originally was introduced as a framework in which to study sort of recurring structures in a sort of very axiomatic way. And so when we see all of these examples of flavors of category theory with the same definitions, the same theorems, essentially the same proofs in many cases, we want to find some way in which we can prove these theorems once and for all and get each of these flavors for free. And this is the most motivation of formal category theory. So it's sort of in a line, formal category theory's application of the philosophy of category theory to category theory itself. And the traditional way this is done is by studying, using two-dimensional category theory to study one-dimensional category theories and the various flavors I mentioned. So that's the sort of overview, but how do we do this more concretely? So what's the appropriate setting in which to study formal category theory? Well, first of all, any such setting should take into account the fundamental intrinsic structures that are present in the theory of categories. So some obvious structures we care about are categories, functors, natural transformations. These are things that appear everywhere, so obviously we need to have some theory that subsumes these structures. And so an obvious candidate then is the structure of a two-category, because a two-category axiomizes exactly this structure. And indeed, in the sort of early days of formal category theory, this was traditionally the approach that was taken. We'd fix some two-category with some property-like structures like limits, colimits, exponentials, etc., and then try to study category theory formally inside the two-category. However, it turns out that the setting of a two-category is insufficient to capture many concepts we care about, especially in enriched category theory, but even in ordinary category theory. And so some examples are weighted limits, weighted colimits, pointwise scan extensions, pre-sheaves, and very importantly for this talk, relative junctions. So we can't define a relative junction in a two-category in such a way that we recover the notion of enriched relative junction. And so when we look at these definitions, we want to identify what they have in common that means two categories aren't sufficient. And it turns out that all of these definitions are defined using the HOMs of categories, the HOM sets in the ordinary category, the HOM objects in the enriched category, so on. What structure do the HOMs of a category form? Well, the answer is a distributor, which is also known as a profunctor or a bimodule. So for ordinary categories, a distributor from A to B is the same as a functor from B op times A into set. But we won't need to worry about the concrete definition. So the sort of summary of this slide is that to really capture theorems of interest in category theory, we also need to take into account the structure of distributors. So then we ask ourselves, well, what structure do categories, functors, and natural transformations and distributors form so that we can study category theory formally? And the first obvious answer that jumps out at us is a double category. But it turns out that double categories aren't going to be sufficient to study enriched category theory. And the reason is that distributors, in general, don't compose. And the reason for this is that we usually compose distributors using some co-end expression, which requires us to have enough colimits in our monoidal category V. And in fact, even if we're just interested in ordinary category theory, we still have an issue with composing distributors when we're working with large categories rather than small categories. However, this is not the end of the story. There's a solution to this. So, although we can't necessarily compose distributors, because distributors are composed when the composite exists using colimits, we can axiomatize what it means to map out of a composite. And axiomatizing this situation leads to the concept of a virtual double category. So let me explain what a virtual double category is. So in a strict double category, we have two classes of one cell. So I'm calling them loose cells, which correspond to distributors, and tight cells, which correspond to functors. And in a strict double category, both of these can be composed strictly associatively and unitally. Now, a pseudo-double category generalizes the situation. So we can still compose both tight cells and loose cells. The composition of loose cells is only associative and unital up to coherent isomorphism. A virtual double category generalizes this further, so we can't compose loose cells at all, but instead we generalize the shape of a two-cell so that it has a multi-array domain. And so the notion of virtual double category is to a strict double category as a multi-category is to a strict monoidal category. So if you're familiar with the theory of multi-categories, the theory of virtual double categories behaves very similarly. And so it looks maybe a little intimidating first, but it's sort of very natural to work with. Now, if we want to claim that virtual double categories are the appropriate setting for studying enriched categories or flavors of category theory in general, we need to show that they actually form a virtual double category. So I'm not going to go into the details here. I just want to point out that there is a very natural notion of multi-array two-cell between distributors. It's called a V-form. It was originally introduced by Day and Street. And yeah, I won't go into the details. The one thing I'll mention is that when we take null-array two cells with identity codomain, these are the same as V natural transformations. This is a generalization of the concept of enriched natural transformation to multi-array domain. And indeed, V categories, V functors, V distributors, and V forms form a virtual double category, VCat. And the important thing to note here is that V can be pretty much anything. V can be a monoidal category, you can take V to be a bicategory, V to be a virtual double category, we still get a virtual double category in the end. So it really seems like this, the setting of virtual double categories is enough to capture many flavors of category theory. Now, the virtual double category of V categories is very well behaved. So in particular, although we don't have binary composites of loose cells, we do have nullary composites. So we have identity distributors, which are given by the Hom sets or Hom objects of a V category. And we can also restrict distributors, both in their contravariant argument and their covariant argument along functors. And again, it's not particularly important understanding this. This is just a two pieces of structure that are very important to do anything with in formal category theory. So this situation was axiomatized by Truckwell and Schulman in 2010, and they called these virtual equivalents. And these are analogous to per equivalents of wood, for instance. So when we have all composites of loose cells, then this is the same as a pseudo-double category with companions and conjoints. So now in the last part of the talk, I'm going to explain how these two aspects come together. So first of all, the definitions of relative monad and relative junction generalize very directly to the context of the virtual equivalent. So all we do is we take the definition and we replace category with object, functor with tight cell, distributor with loose cell, and form with two cell. And then we can instantiate this in various equivalents of interest to get different notions of relative monad. So relative monad in the equivalent of V categories is a V-enriched relative monad. A relative monad in the equivalent of internal categories is an internal relative monad. A relative monad in the equivalent of V categories is a V-strong relative monad, and there are many other examples. And then we can do much of the basic theory of relative monads that's known in the ordinary setting, in its formal setting. So some examples are every relative junction induces a relative monad. Left relative adjoint preserve those colimits that are preserved by their root functor J. Right relative adjoints preserve the limits when the functor J is dense. And if we have some monad on some object, we can precompose by a tight cell to obtain a new relative monad. And so one thing I don't want to give is the impression that we're just doing the ordinary theory of relative monads in a formal setting. We actually get a lot of new results too. And some of these results are facilitated by working in a formal setting. And by that I mean, when you're working in a formal setting, you have less structure to work with, and this often reveals the kind of shape that statement should take, because you can't use any unnecessary structure, you can just use what you're given. So one prominent example of this is, well, we all know that a monad on some objects in a 2 category is exactly a monoid in a strict monoidal category of endo 1 cells on that object. And in fact, something similar is true for relative monads too. But we have to go to slightly more general structures. So if we fix some tight cell J, so functor for instance, then there's a skew multi-category whose objects are exactly the tight cells from A to E. So I'm not going to explain what a skew multi-category is. If you're familiar with skew monoidal categories, this is a generalization. But it turns out that monoids in this skew multi-category are precisely J-relative monads. So just as ordinary monads are monoids, so too are relative monads. And this generalizes a theorem that is well known from the ordinary context, where if we have enough point-wise left extensions lying around, we actually do get a skew monoidal category. Okay, so now I'm coming to the last few slides. And I want to answer a question that may have occurred to some of you who are familiar with some formal category theory. And so one of the earliest works in formal category theory was Ross Street's formal theory of monads, where he developed a lot of the theory of monads in the setting of a 2 category. And so in particular, if we just care about ordinary monads and not relative monads, there are 2 approaches we can take. We can either work in a 2 category at a street, or we can work in a virtual equivalent. And so there's an obvious question, how do these 2 approaches relate? And it turns out that even if we're just interested in ordinary monads, so if we're interested in relative monads, we need an equivalent even to state the definition. But if we're just interested in ordinary monads, we can state this in a 2 category. However, there are some theorems that require distributors to state even about ordinary monads. And so there's some examples of results that we can obtain about ordering monads in a formal setting that are impossible to obtain in a 2 category. So some examples of this are left adjoints preserve weighted colimits, forgetful functors create weighted limits, a monadicity theorem, algebras, and the theorem that algebras arise the co-completion of the 3 algebras. These are a few results. And to prove these results in a setting of equipment, we have a notion of algebra object for a monad, and indeed a relative monad, which is stronger than the definition of an algebra object in a 2 category, our street. And the important thing about this universal property is it satisfies a double categorical universal property. So it satisfies a universal property with respect to loose cells as well. And this allows us to prove the theorems on the previous slide. And so I'm going to end with this, this result. So one of the theorems we've proven is that if we fix some tight cell J, then a tight cell U, to be thought of as sort of a forgetful functor, is J relatively monadic, if and only if U has a right J relative, sorry, that should be left, if U is a left J relative adjoint and creates J absolute colimits. And so when you take J to the identity, this recovers Pare's monadicity theorem, and it works in the enriched context as well. And this theorem is new even for ordinary relative monads. So although our motivation is enriched category theory, a lot of our results are new even for ordinary relative monads. So I'm going to stop here. I just want to quickly summarize what I've said to refresh it in your minds. So really been 2 aspects to the talk. One is just sort of introducing those of you who have not heard about relative monads to relative monads. I haven't had time to talk much about them specifically, but it's useful to know they're out there. The second point is that we can generalize many of the theorems from ordinary category theory, enriched category theory, internal category theory in a single setting by working with formal category theory. But 2 categories are not sufficient to study many of the theorems we care about, and so this is why we work with virtual double categories and virtual equivalents. So we have 2 papers on arXiv about this at the moment. The first paper we sort of lay the groundwork, do a lot of the basic theory, and the second paper we study relative monadicity theorems. And these are the first 2 of a series that are to come. So thank you very much for listening.
Thank you very much. Maybe I can just ask for clarification on the previous slide.
Yeah.
The word dense appeared.
Yes.
I missed what it means.
So there are many equivalents of definitions of dense. So for functors, one definition of a dense functor is that it's a nerve functor. So if you have a functor from A to B, then the nerve is the induced functor from B into pre-sheaves on A. So if this nerve functor is fully faithful, then the original functor is dense, and vice versa. Another definition is if you take the left can extension of J along itself, then it's the identity. And this is an assumption that we really need for the monadicity theorem. In fact, for much of the theory of relative monads, we need density, but the identity functor is dense, so this does capture the ordinary monadicity theorem.
Thank you.
Yeah, thank you.
So, first question is
here. About these virtual double categories. So you said it's a setup for formal category theory. So what about the unadal and unadal embedding there?
Right, so that's something I haven't had time to talk about. So it's possible to define a notion of pre-sheaf object in a virtual equipment. And this has been done by Rolf Kuenberg, for instance, in a slightly more general setting. And so one can prove various theorems about pre-sheaves, about co-completions in such a setting. So there's a universal property of a pre-sheaf object, and this captures the sort of ideas you're thinking about. Yeah.
And also, what about using instead unadal
structures?
Unadal structures.
Right. So
what is the connection with this?
Yeah. So unadal structure is another approach to formal category theory. Instead of axiomatizing the structure of distributors, they axiomatise the structure of the pre-sheaf instruction. Now, the reason we work with virtual equivalents rather than unadal structures is that unadal structures require some notion of pre-sheaf. And so, for instance, if you're working in a setting of enriched category theory, for a monoidal category that doesn't have enough structure, you may not be able to form V categories of species. And so UNAIDS structures are less general than virtual equipments. They don't capture all of the examples we're interested in, and that's why we work with virtual equipments.
There's a question up there, yes.
So, did you ever consider the basis of your enrichment to be a closed category which is not necessarily monolithic? The reason why I ask is connected with monad structures because every monad structure on the 2 category is an enriched category, and it is enriched in the closed category in the sense of binary and cap. So, did you ever consider to develop the setup in this
Yeah, thanks. So, actually, although in this talk I haven't been specific about examples, but in our paper we spell an example of enrichment in a monoidal category very explicitly. However, we've actually developed lots of the theory in the more general context of enrichment in a virtual double category, and this in particular subsumes the setting of closed categories. So we have considered it, yes. I can talk more in detail afterwards if you want.
One more question there, yes.
Yeah, so this setting, you mentioned before the theory of the streets theory with monads in 2 categories. Looking forward to n categories, one way we sometimes enter that theory is we say that 1 categories are situated within a 2 categories. The reason I like to look at them, and then 2 categories are situated within 3 categories. The reason I like to compare them. This idea of a virtual double category to me suggests a different induction where you go from 1 category to virtual double categories. Do you have some idea of a natural setting or context where virtual double categories exist and should be compared?
Yeah, great question, thanks. So the setting of virtual double categories is more analogous to the sort of n-fold category approach, where you go from double categories to triple categories and so on. However, you have to generalize slightly further because in triple categories you do allow like strict composition at all 3 dimensions. So the precise answer is that no one has studied the 3-dimensional version of this yet, but one would go in this direction and needs to work out the right notions of composition, etc. So I expect it can be done, but no one's thought about it yet.
Okay, thank you.
Okay, there was one more question there.
It's a very short question. But first of all, let me thank you again. It was very nice. Do you have any way to relate there is this very useful way to formally do monad theory with lax functors. Monad is a lax functor from the ball. Do you have anything similar for relative monad?
Thanks for the question. So this is quite a subtle question, and so if you remember on one of the slides, I mentioned that monads are monoids in the monoidal categories, but to study relative monads in full generality, we need to always skew multi-categories. And so I expect something like that is possible, but one needs to generalize skew multi-categories to something functorial in some sense. And so I don't know exactly what that would look like. It would be interesting to try to work it out.
Okay, thank you. So let's thank the speaker again.